Hi and welcome to video 3 on this series on Unit 4 Topic 1 Financial Maths from the General Mathematics course. And in this video we're going to talk about compound interest. In the last video we talked about simple interest, so it's just a build up from the simple interest video. Compound interest has been covered in Unit 1 Topic 1. We also talked about it in Unit 3 Topic 3 Sequence and Series, and you will have talked about it in Year 9 and 10 as well. So compound interest is interest where you earn a certain amount of interest, a percentage of your first year's investment, but then that gets added on. So the next year you earn interest on your investment and the interest that you had previously earned. So the interest that you're earning is growing over time as well. So you get to see this as we move forward. It is a geometric sequence as opposed to the arithmetic sequence that is simple interest. And here is the standard formula in light blue, just so you can barely read it. And that standard formula is really common. The P is the principal, the I is the interest rate, the N is the number of time periods, so they have the same meaning as the simple interest. And A is the final value, the future value, the maturity amount, the value of the loan or the investment or whatever. So you'll see A a lot as well. It's really important that you recognize this. Simple interest gets you the interest rate. Compound interest gets you the final value. Now it's very easy to go from simple interest getting you the interest earned and adding that to the principal to get the final value. So it's not a big problem, but that's what happens there. We could adapt the formulas for sure, but this is the standard, so it's worth getting used to the standard. The final value for a simple interest formula is equal to the principal plus interest, and that means that if you wanted to compare the interest earned, well, that would be A minus P. So this is the one that you would use for simple interest to work out A. This is the one you'd use for compound interest to work out I. So be careful when comparing. You have to have converted one of them. Okay, so here's an example stolen from above. I've just cut and pasted and I've crossed out simple and put compound there. Consider an investment of $1,000 earning 8% compound interest per year. Starting at $1,000, the final value was A equals P plus 1 plus I to the power of N, P times 1 plus I to the power of N. So if we leave N open, we could make N 1, 2, 3. Eventually we're going to do a comparison where N is 5, and you might be given a question where you're told what N is. Then when we leave N open, we can actually see a couple of things. So you might recall that in a geometric sequence, term N was equal to A R to the power of N minus 1. Well, we've kind of got that A, R, and this is a little bit out of sync, but N minus 1 is just one step out of sync. So by leaving N open, we're actually determining the R value. The R value is really important. It's our constant multiplier. It's our growth rate, our growth factor. It's the thing that you multiply by to see how it's growing. Or you might have a decaying series and it might be 0.92, in which case you're losing 8% each time, and it would be decaying over time. But we've got our constant multiplier, so we start with 1,000, and we can use our calculator skills here again. Type in 1,000, enter, type times 1.08, enter, you get 1,080. Enter again, you get 1,166.40. Enter again, you get 1,259.712. Enter again, and you get my answer again. You get my answer again, because we're just multiplying by 1.08 each time. It's our constant multiplier. And of course, if we wanted to find the 5th year value, we could always go to the formula here, and by substituting in the formula, we would get that $1,469.33 if we needed to. And there's what I've just been talking about in the calculator. But that builds up an understanding of how this relates to geometric sequences. And that's going to be an important relationship because it's a good way for them to incorporate a complex familiar or complex unfamiliar question into an external exam. And now time for some light-hearted entertainment.
What is the best angle to tackle a maths problem? The triangle.
Now here's something interesting as well. After 5 years in the same investment, same rate, simple interest was 1,400, compound interest was 1,469.33. That should always be the case for these savings account situations, because compound interest, you are earning interest on your interest. So compound interest is better in the long run in that respect. Let's have a look at an example. Amanda invests $2,700 at 4.3% per annum compounded yearly. What will be its value when the investment matures? That should say matures, but it's got a Y hanging through it. Well, maturity, first of all, I've written a little thing over here. An account matures when it ends. If you have a fixed rate account or you have a savings account that's locked in for 5 years, it matures after 5 years. So it's a financial term. So Amanda's investing, P equals 2,700. I equals 4.3 over 100, which is 0.043. And what will the investment be worth when the investment matures? So we haven't been given a year value, so we might actually incorporate one into the question. But let's start by thinking about this generally. Well, the amount is equal to P times 1 plus I to the power of n. That's equal to P times 1 plus 0.043 to the power of n. And of course, P is 2,700. 2,700 times 1.043 to the power of n. Now, if we wanted to know what it was worth when it matured after, say, 10 years, then the amount after 10 years, A10, would be 2,700 times 1.043 to the power of 10. And that would be equal to $4,113.46. So you could work it out for a particular year as well. But if it doesn't give a year, then it might be asking you to do it generally, which means you just leave the N on there. All the best.